Okay, my name is Ali Ibrahim. After spending over 2 decades in the Silicon Valley in California, I joined Alat. I moved to this beautiful city around a month ago, and I'm the VP of Strategy for Semiconductor Business Unit. Now, before delving into the subject of today, I'll give a high-level overview of what Alat is. So Alat was founded in 2023 with the headquarters here in Riyadh. Our mandate is really to create a manufacturing hub in Saudi Arabia for electronic and industrial products. It's 100% owned by the PIF, and we have 9 business units. And these business units really cover a wide range of product, from semiconductor to smart devices, to smart building, all the way to next generation infrastructure, as well as AI infrastructure. We have different partnership models, and some of the collaboration that were announced last year and this year is a collaboration with Lenovo to build manufacturing for PC here in Saudi Arabia. The collaboration with SoftBank to build robotics here in Saudi Arabia, as well as the collaboration with Carrier to build HVAC system here in Saudi Arabia as well. So at a high level in the semiconductor, we have a hybrid approach. We have the IDM foundry approach, we have the pure play foundry approach, and we have the chip packaging approach. On the IDM foundry side, really we focus on 3 areas, power, perception, and processing. And in terms of fab, our current focus is really 28 nanometer and 40 nanometer. We collaborate very closely with the National Semiconductor Hub. Some of the collaboration includes providing manufacturing support whenever possible, as well as really leveraging the design expertise whenever possible as well from the NSH. We work very closely with Dr. Navid on this area. Okay, next one. All right, switching to the main subject of today. You know, as a system designer, when you're trying to build your next generation roadmap, you have to worry about many things. But we can lump these things into really 4 categories. How can you achieve the required performance for your emerging workloads? How can you reduce the power consumption, or at least be within the power budget allocated to you? How can you reduce cost? And cost has multiple components. There is the R&D cost, there is a fabrication cost, and there is a product cost. So we have to worry about all 3 of them. And finally is the time to market as in scalability. And what scalability means is we will not worry only about putting the first product in the market. We have to look about the entire product roadmap where you could have multiple product segments into it. So as we are building our product, we really want to make sure that the design we start with is scalable enough to cover our entire range of roadmap. Now, what was shown is that, as I'm showing here in the top left diagram, is that to really, especially for the server CPU and the server GPU, to achieve this required performance, especially with the slowing down of Moore's Law and the insatiable demand for compute power by the emerging AI workload application, the die area is increasing and is really approaching the theoretical limit. And this has a lot of implication on yield and, as a consequence, the cost of the product. And what AMD showed in the diagram underneath it, you can see that the cost per yielded mm square is increasing over time. So we need a solution to help us address this yield issue, and that's where chiplet really come into picture. So what is chiplet? What I'm showing here at the bottom is a monolithic die. So in a monolithic die, you have all your IPs in it. You could have a CPU, a GPU, a fabric, a memory controller, and so on and so forth. So the idea here is that we chop it into multiple pieces. And by doing so, your yield will improve, hence your performance per dollar will improve as well. So this is really the idea in principle. And there is also another benefit, because once you go toward chiplet, you don't have to use the same process for everything. Like if you look at the monolithic die, for instance, and if we are using the latest and greatest process, all your components, digital or analog, have to be in that process. With chiplet, we can use the right process for the right logic. So for instance, for your CPU IP or your GPU IP, you might go for the latest and greatest process. But for the analog macros, as an example, and these do not scale very well going from one process to another, you can use an N-1 process. And this also has another benefit with cost. Basically, your performance per dollar is improving. The other benefit is that scalability, which I highlighted a little bit earlier. If the architecture is designed correctly, you can, in theory, stamp this chiplet. You can stamp multiple GPUs and multiple CPUs, and this would allow you really to cover your entire roadmap in terms of product segmentation. Now, if you look at the market penetration today, as expected, you have the HPC and the PC is the higher penetration for the right reason, because the die area in these products are really big. And so to address the performance per dollar, for HPC and PC, you could see an increase of chiplet adoption. As far as the consumer and the automotive, it's right now it's slow, but we expect it to increase over time, especially as consumer products start using more and more expensive process over time. Okay. If you look at it, it doesn't come for free. There are a lot of challenges when you move to a chiplet design. For instance, the design complexity, it becomes higher. You have to worry about really chip-to-chip communication. What sort of protocol we use? What is the physical layer? The other area we have to worry about is really the power consumption, because once you cross from die to die, depending, again, on the physical layer, the connectivity you use, the power consumption could be high. Latency is a problem, so we want to make sure really when we, from an architectural perspective, when we develop this chiplet, we have to worry about the type of workload and how they get impacted. And the most critical part right now is really packaging. What I'm showing here on the right side is 3 different types of packagings. So the top one is called the 2D packaging, where we have multiple chiplets. We connect them over the substrate. So all the communication happens over the substrate. The second one is really 2.5D. And the main difference is that the communication happens over an interposer. There are different types of interposers that can be used. In this case here, silicon interposer. Last one is this 3D packaging. And in this case, you stack multiple dies together. And the stacking could be really TSV, could be hybrid bonding. There are other technology as well. Now, which one to pursue, it really depends on many factors. The product you have, the number of chiplets you have, the communication you need between these chiplets. So all of these have to be taken in consideration when designing your new product. Now, of course, as you could see, is that while we try to improve our performance per dollar to move to our chiplets, we are adding cost from a package perspective, because these are really complex techniques. And most importantly, we have to be really, really careful that our overall system yield doesn't offset the benefit we have from going through chiplets. So it's extremely critical. Now, from a system designer perspective, it's changing the way we do our roadmap. Right now, you are not just thinking about the silicon. Now you have to worry about the entire system level from a planning perspective. It's a co-design between IC and package. Okay, proprietary chiplets are out there. And in fact, if you look at AMD, for instance, they have AMD Ryzen, EPYC, the MI250, the MI300. My favorite one is the Intel Ponte Vecchio, because I worked on it. And as I'm showing here, like 2 diagrams, you have the Intel Ponte Vecchio, which has 47 chiplets. They are 3D stacking using Intel Foveros technology. And the bottom one, we have the Intel Meteor Lake, which is for the PC segment. By the way, the top one is for HPC. This is a high-performance GPU used in the Aurora supercomputer, if you are familiar with it. The bottom one is in the PC segment. And you can see really the differences between them, like 47 chiplet, 3D stacking versus the 4 chiplet on top of a passive interposer. So as you could see, really, there is a common theme in all these products. They are developed by single vendor product. What that really means is that the same company design everything, the same company own the end-to-end test, yield, supply chain, warranty. And of course, the side effect of this is that there is a higher R&D cost, limited in focus, because this company focus on their products only. There's a time to market, custom interfaces, you're locked into a single vendor, and of course, limited customization. And that's why there is really an increased need for a chiplet ecosystem to help address many of these challenges that we are facing. But of course, to achieve this chiplet ecosystem, standardization is a must. And standardization really in many areas. So in the interfaces side, in the system side, manufacturing flow, business flow, and so on and so forth. Okay, so in the industry today, there are many efforts when it comes to standardization. I'm just highlighting some of them here. The Universal Chiplet Interconnect, or UCIe, this consortium really focuses on the die-to-die, both the physical and the protocol layers. And they have different type of interconnect depending on the packaging you are using, whether it's a 2D or 2.5D or a 3D. ARM chiplet system architecture, they just released actually their first spec around a month ago. They're focused really on the system partitioning and chiplet connectivity, and how can you reuse these chiplets into different product segments. This is really the focus there. Open compute, on the other hand, they go beyond the design side. They're also focusing on the design and manufacturing flow, which is extremely critical. And they're also focusing on the business workflow model. As I said earlier, when you have these different chiplets coming from different vendors, and you have a problem in yield, who pays for it? Does the chiplet provider pay for it? The company that's building the product pay for it? Or the manufacturing itself pay for it? So all of this issue from a design perspective, from a manufacturing flow perspective, as well as a business perspective, they have to be addressed to have an ecosystem for this chiplet. There is what I call is a hybrid model, or a partially open. And the one, for instance, proposed by AMD. And in this approach, really, it combined both proprietary chiplets as well as chiplets from the open ecosystem. However, it's a single vendor, and the system architecture is owned by that particular single vendor. It's a hybrid approach. Finally, there are other collaboration between different companies, like the one between Bosch and Tesstorent. Tesstorent is a startup company in Toronto, and they are focusing on the standardizing really the chiplet in the automotive segment. In short, in the short term, I really expect more adoption of a hybrid approach, whether it's a single vendor or multiple vendors collaborating together to put out there like a custom product. In the mid to long term, I will see like a move toward more fully open system. And this is good for all the local startup here. And I think the idea is to help create a local, vibrant ecosystem for chiplet here in KSA. And we'll be working very closely with Dr. Naveed to make sure that this become a reality here. Thank you so much.